Now that we have examined the graphs of the 6 basic trigonometric functions in great detail, let's pause and review the basic properties of the parent functions we've learned. In 2.4.3, we'll take a look at the function gallery for trigonometric functions. We'll begin by examining the graphs of y equals sine of x and y equals cosine of x. Because both of these functions complete one fundamental cycle in a distance of 2 pi units on the x-axis, the period of each of these functions is 2 pi. Whereas sine of x takes a roller coaster shape in its fundamental cycle, cosine of x follows more of a bowl shape. Each of these graphs contain 5 key points. For sine of x, there's an x-intercept at the beginning and end of the period, and at the midpoint, we find another x-intercept. Halfway between the two x-intercepts, we hit the maximum point, and at the midpoint between the last two x-intercepts, we see the minimum point. Though we are only looking at one fundamental cycle of the graph of sine of x between 0 and 2 pi, the domain of sine of x is negative infinity to infinity. That is, this one fundamental cycle is periodic, repeating across the entire x-axis. The range of sine of x goes from the minimum y value of -1 to the maximum y value of 1. The 5 key points of cosine of x are also arranged logically. At the beginning of the period and ending of the period, cosine attains its maximum value of 1. At the midpoint between the first and last points, cosine attains its minimum value of -1. Halfway between the maximum point and the minimum point, cosine has an x-intercept. Similarly, halfway between the minimum point and the ending maximum point, cosine also has an x-intercept. Like sine of x, even though we're only viewing one fundamental cycle of cosine of x, the actual domain of the function is negative infinity to infinity. That is, this bowl shape repeats itself periodically across the entire x-axis. Also similar to sine of x, the range of cosine of x is from y equals -1 to y equals 1. Once we have a good understanding of the graphs of sine of x and cosine of x, we can also examine the graphs of their reciprocal functions, cosecant of x and secant of x. Recall that cosecant of x is the reciprocal of sine of x, and secant of x is the reciprocal of cosine of x. For this reason, everywhere that either sine or cosine has an x-intercept, that is, it has a value of 0, the reciprocal function is going to be undefined. So notice here you can see the graph of sine of x, and at every place where sine of x has an x-intercept, the corresponding graph of cosecant of x has a vertical asymptote. That is, cosecant is undefined at those locations. Where sine of x either has a value of 1 or a value of -1, notice cosecant of x shares those points. And again, because of this reciprocal relationship, cosecant proceeds in the opposite direction of sine. So where sine is increasing, cosecant is decreasing, and vice versa. Having a good understanding of the basic graph of sine of x, we can then derive the corresponding graph of cosecant of x. Now, like sine of x, cosecant of x has a period of 2 pi. The asymptotes are located at integer multiples of pi. So we're going to express these equations as x equals k pi, where k is an element of the integer. Thus, the domain in interval notation is the set of all x, such that x cannot be equal to a multiple of k pi, because that's where cosecant would be undefined. The range of cosecant is expressed in two intervals. The lower half has y values between negative infinity and -1, and then we unite that with the interval of the upper branch, which goes from y equals 1 to infinity. This similar relationship exists between secant and cosine. If we know the basic bowl shape of cosine, then we can assume that everywhere that cosine of x has an x-intercept, secant of x will have a corresponding vertical asymptote. where cosine of x has a value of either 1 or -1, secant of x will share that same value. And like cosecant and sine, where cosine is decreasing, secant is increasing, and vice versa. So the better understanding we have of the graph of cosine and the relationship between secant and cosine, then we can intuitively derive the graph of secant. Like cosine, secant has a period of 2 pi. The asymptotes are located at odd integer multiples of pi over 2. We express this as x equals 2k plus 1 times pi over 2. Recall that if k is an integer, then 2k is an even integer. Therefore, 2k plus 1 generates an odd integer reliably. The domain is everywhere except where these asymptotes occur. In set builder notation, the domain is the set of all x, such that x cannot be equal to an odd multiple of pi over 2, expressed as 2k plus 1 times pi over 2. Again, the notation that k is an integer is essential. Secant and cosecant have the same split range, that is -infinity to -1, united with 1 to infinity. Those four graphs all share something in common. They all have a period of 2 pi. Tangent and cotangent are set apart as being a little bit different. Both tangent and cotangent have a period of pi. One fundamental cycle of tangent ranges between -pi/2 and pi/2. In that interval, we can observe that tangent is an increasing function. Halfway in between those first two asymptotes, tangent crosses the x-axis. Between that x-intercept and the rightmost asymptote at the midpoint, tangent attains a value of 1, and at the midpoint between that leftmost asymptote and the x-intercept, tangent attains a value of -1. So these are the three key points that are useful in recognizing the graph of tangent. Now, because the distance between the asymptotes is equal to the value of the period, we can express the equation for all of the asymptotes for periodic tangent across the entire x-axis. We can make the simple observation that the asymptotes occur at odd multiples of pi/2. So as we did previously, we can express this as x equals 2k plus 1 times pi/2, where k is an element of the integers. Therefore, the domain of the entire tangent function is the set of all x, such that x is not equal to 2k plus 1 times pi/2, where k is an integer. The range for tangent is distinct from the range for all of the other trig functions. It ranges from -infinity to infinity. Now, comparing that to the graph of cotangent is a useful way to understand its nature. Where tangent was increasing, cotangent is decreasing. We can also see that even though the period is pi, the fundamental cycle of cotangent is shifted just to the right of the fundamental cycle of tangent. This fundamental cycle occurs for the argument between 0 and pi, the location of cotangent's first two vertical asymptotes. Noticing that those asymptotes occur at integer multiples of pi, we can express the location for every asymptote in the form of x equals k pi, where k is an element of the integers. Thus, the domain of cotangent in interval notation is the set of all x, such that x is not equal to an integer multiple of pi, or k pi, where k is an element of the integers. And like tangent, cotangent also has a range of all real numbers, or -infinity to infinity. These basic facts and properties are essential for your mastery of the graphs of the trigonometric functions. Now, if that stresses you out, how about a little bit of a release? Here's a snapshot of not only our new trigonometric functions, but the functions that you know from algebra. You remember the good old days of examining your algebraic function y equals x, your parabola y equals x squared, your absolute value v function, maybe even a radical function or a rational function. Well, now you can add to that your roller coaster sine wave, your bowl cosine wave, and your tangent function, which looks a lot like a cubic function. If you can turn those into dance moves and release a little stress, then more power to you. Now, don't forget the graph of the unit circle given by this lovely equation. And I don't know, maybe you feel like this at the end of this section. But we have successfully completed our study of trigonometric graphs.